Welcome to Talk Universe. I'm your host, Sir Charles Schultz, and this is our show for Wednesday, December 28th, 2016. Tonight's show is free energy. We've all seen the ads about machines that produce all the energy you could use for your home or your vehicle for free without consuming fuel for an indefinite period of time. We're going to look at just exactly what energy is, whether these sorts of devices are realistic, and what the idea behind them might be. Where does energy come from? How do we use it? How is it stored? And can we get an unlimited supply of energy without any effort? This is exactly what our show is about tonight, so sit back and enjoy the ride. I'd also like to welcome our new listeners in Anguilla and in Ireland and in Jordan. I hope you're enjoying the show, and please submit your comments and we'll take them on the air. I also want to thank our new subscribers and wish everybody a Merry Christmas and Happy Holiday season. This has been a very tumultuous year. I think a lot of us will agree that some things we never expected have occurred, and it's just been one of the most amazingly chaotic years that I've seen. Let's hope that 2017 will be a much better year. This is the last show of the season, so I will say a few words about that, but let's hope for a better year. I know that we're all looking forward to something a little better than what we've seen. So let's get right down to it. We all know that we need energy to run the things around us, and we know that energy exists everywhere. The question is, why do we have to burn fuel to get energy, or run a nuclear reactor, or do any of the things we do to generate the power to operate things? And it's a very simple thing. Everything requires some effort, and that effort has to come from somewhere. So energy is what we use to transform or move things. Now, energy in itself comes in a number of different forms, and basically what it is, it's the potential to transform something or move something. It's the potential for change, and it has a finite amount. There is a certain amount of energy in the universe, but it can fool us because energy is not created or destroyed, but it can be transformed. Many people are aware of the Einstein equation, E equals mc squared, and what does that really mean? It really means that energy is equivalent to mass, and mass and energy are the same thing. So you can swap mass for energy or energy for mass. It isn't typically easy to do, but that's what nuclear power does. And we'll discuss that a little bit too. What we're really going to stick with is the more common forms of energy that we deal with and how we power all the devices we have and the sources of that energy. And we're going to look at the possibility of getting that energy for free. A lot of people talk about that, and it's a hot topic right now because the cost of energy is very high. Everything we do is determined by available energy, from making clean drinking water to running the lights in our home to growing food. So energy is an exceptionally important thing, and we do need to start confronting the fact that it appears to be limited, and yet we'll talk about that. We'll talk about limits and open and closed systems and where the energy comes from and goes, because as I was stated, it's neither created nor destroyed. It ends up somewhere else. But sometimes it's in places where we just can't get to it. So we'll talk about that, and we'll see what it takes to get energy. So one of the things we have to look at is the content of energy in a system, such as the Earth. You can imagine if you lived in a closed box and you had to depend on just what was in the box to provide for you, that in a little while, if you didn't have some sort of oxygen, you'd run out of air. And in the real world, of course, plants make the oxygen that we breathe. You also know that if you had just a certain amount of, let's say, diesel power to run a generator, once you'd used up that diesel fuel, your generator would no longer run. So within the system, there would be a fixed amount of energy, and it would go from dense, usable sources downhill to waste heat pretty quickly. And at the end of that period of time, unless you have some sort of a system moving that energy back uphill again for you, creating more of it or supplying it, you're going to run out. There is a fixed amount, just like a charged battery. The battery doesn't create energy, it simply stores it. Well, any closed system has a limited amount of energy available for use in it. And as the energy is being used, the amount of entropy or disorder in the system increases to the point where the energy is no longer available. It's in a form you can't reach anymore. Waste heat, generally. So here we have two ideas that we've covered. Number one, a closed system has a fixed amount of energy in it, and it doesn't change. When it's used up, it's still there, but here's the second concept. It's disorderly. Entropy. The randomness or disorder is an important part of the picture. If the energy is in the system, but it's in a form that's too disorderly to use, then it's not accessible, and therefore, for all intents and purposes, you can't use it. So the concepts of energy and entropy are tied hand in hand. Potential to do something and disorder. You have to have a system that has order to it, or you won't be able to do anything with it. And our lives consume order and create disorder. And even though our bodies are complex structures, and they're left behind at the end of the process, there was energy consumed to create them, and there's always a loss. You know, it's like the old adage, you can't win and you can't break even, you can only lose. That's entropy. So the question is, how does anything of complexity or order show up on the Earth? Well, the answer is very simple. The Earth is not a closed system, and this is one of the first mistakes that a lot of people who are not scientists will make. The Earth is an open system, and its energy is being provided from a couple of different sources. Now, one of the sources is inside the ground itself, geothermal energy, the heat inside the planet. And one of the sources really also tied to the Earth is the chemistry that's in the Earth. Oil is a chemical method of storing energy, and we'll get to the different types of storage of energy and different types of energy shortly here. But oil is like a battery. It's a chemical way of storing energy. But the biggest contributor to life on Earth is the sun. And the sun is certainly outside of our system. It's something we don't control, and it's immensely powerful. And it puts all the energy in our environment to drive the weather and to drive biology and to drive photosynthesis. So we are not a closed system. We're getting an incredible dose of energy constantly from the outside, and that's what powers everything. How do we know this is true? How do we know the system works the way we say it does? Well, it's because so many experiments and measurements have been taken and repeated time and again. We have never seen a violation of this system, except sometimes small quantum level effects, and we'll get to that also because there's very interesting things to see about that. There's never a violation of the system at the macro scale, at the scale that you or I live. So we know, because of the ability to perform these experiments under different conditions, different people, different rules, and the results are always the same. When you see a scientific theory, you know that it's something that, when it's accepted as being truthful or factual, we know that it's something that's been done so many times, people are pretty darn certain they haven't found any loopholes to it, and that becomes a law of science or a law of physics. But another big part of the process that a lot of people miss is generating a theory that explains how and why, and making a mathematical model of that theory, and doing the experiments to test that theory to see if it matches the model, to see if the model is consistent and makes sense. And so we do have rules and models that make sense, and we also know that starting with supercomputers, if we take those rules and put them in the system and then run what occurs, run the simulation, the results match reality very, very, very closely. So we know that it's not just something that's made up. We know that there's an underlying structure, and we know that the rules work properly, and we have a mathematical solution to it and a modeling solution that matches very, very closely. And as our understanding gets better and the experiments get more to the point, we'll discover more and more about it until eventually we will solve the system. We'll know what it is, because after all, there's only a finite number of facts in the universe, which indicates that we should be able to figure the rules out. And one of the holy grails of physics is to come up with an equation that you can write on a napkin or the back of a business card that explains it all. And we're very, very close to that, believe it or not. So from these experiments, we got a set of rules, but we also have determined different forms of energy, different types of energy. And the most commonly known one is kinetic energy. And what that is the motion of a body. Whenever anything is moving, it has an amount of mass. The object has mass. And so the speed at which it's moving carries a certain amount of energy. That's kinetic energy. Now, potential energy is a little different. We've all heard of it. That is energy that is stored in a form that can be released or transformed. Like a spring wound up has potential energy, or a ball at the top of the hill has the potential to roll downhill and release energy. Mechanical energy is usually the sum of the kinetic and potential energies put together for a system, mechanical energy. And a mechanical wave, everybody's seen this. If you have a slinky, let's say, and you shake it up and down, and the spring wobbles, and it has a movement that carries on for a while, that's mechanical wave energy. The string plucked on a guitar waves back and forth. So that's a form of mechanical energy. that's propagated by the material moving or oscillating. Chemical energy, that's a real simple one. We all know that some materials will burn and they'll release heat in the process, and that's chemical energy. That's the energy contained in the molecules of a substance, by the way it's put together. Electric energy, we know what that is. There's electrical power in our outlets, and that electrical energy is literally the movement of charged particles that can perform some work for us. It's sort of like water moving through a pipe. Magnetic energy, of course, and this is the most misunderstood. That's the energy contained in a magnetic field, and a lot of people have the feeling that you can extract power from it. Well, a magnet is no more than a fancy type of spring. And if you take the energy out of the magnetic field, the field collapses, it's gone. You've used it up. You can't get free energy out of magnets. You have to move them around or cause something to happen in order to extract energy. Radiant energy, well, that's light, for instance, radio waves, any sort of electromagnetic energy that's propagating through space. That's radiant energy. And you can feel it from a heat lamp, you can feel it from the sun, you can see it. And there are other forms as well. Gravitational energy, you have something suspended up above a pit and you cut the wire and it drops into the pit. Well, gravity's accelerating, and that's gravitational energy. Thermal energy, this is, like heat energy. This is one of the things we're most familiar with. When you heat something up, it's hot not just for no reason, but because there's energy of movement at the scale of the molecules or the atoms that the thing is made of. And we're going to talk about heat energy or thermal energy quite a bit because it's very important. So, and there are other forms as well, but this is just a good look at some of the basic forms of energy right off the bat, so we know what we're talking about. Now, a lot of people talk about things like psychic energy or spiritual energy. Let me tell you something. The word energy is being used very loosely here. Energy has a quantity and an amount and a type to it. It can be measured, it can be quantified, it can be used, it can be stored. And when people start talking about fluffy or non-scientific things and they assign the word energy to it, tell them to measure it and show it to you. If they can't do that, it's just noise. It doesn't make any sense. And I know I'm going to hurt a lot of sensibilities here, but if you can't quantify it, measure it, you got nothing. Nothing at all. I'm also going to go in depth about this magnetic motor claim that we keep hearing. Let me point something out. Virtually every electric motor is a magnetic motor. There are some that work on sound waves and oscillation and other stuff, but motors, by and large, are driven by magnetic fields. And it works because the incoming electrical power is doing the moving. So the motor doesn't run for free. It takes power. And the amount of power that it takes is the product of the mass of the motor, the speed it's turning, the efficiency that it operates at. And this is another thing. You have a system that generates some power. You're only going to get some fraction of that power out as usable work. There's always loss, no matter what. There is no 100% efficient system for converting energy from one form to another. And the issue comes down to this. Bearings have friction. They're not perfect. If you hear sound, if you see anything vibrating, if you feel heat, any of those things are a waste of the energy going into the system. They are a show of inefficiency. I often see these dragsters, these race cars going down the street, people having these roaring engines, and I'm thinking, they're advertising the worst efficiency possible because a perfectly efficient vehicle would make no sound at all. This is another interesting thought. When you burn fuel in your car, you only harvest about 14 to 30% of the energy in the fuel as useful movement, driving around. All the rest of it is heat and noise, vibration. All the rest of the energy is wasted. So you put a gallon of gas in your car and only between 14 and 30% of the energy in that fuel actually gets you where you're going. The rest of it turns into waste heat, noise, and that sort of thing, vibrations. So that's something to consider. If we wanted to make cars more efficient, we'd have to find some way of getting that extra wasted energy back into forms we can use. And maybe there are ways to do that. There's something for you to think about. Now, after the break, we'll be back on Talk Universe, and we'll start looking at specifics of systems. Enjoy the show. look at a magnet, and it almost seems magical. Some invisible force that you can't feel or touch pushes or pulls something at a distance. What an amazing thing to see, and yet, what is it really? It's a portion of the electromagnetic force being shown in a very specific way. The energy in a magnetic field is trapped by aligning the spins of the electrons in the material it's made of. In iron, which is naturally magnetic, it has a pair of electrons that orbit in the same direction, and they add up their fields. And that tiny bit is all it takes to make the iron attracted to a magnet. And if you line up a lot of the domains, the little crystals inside the piece of iron, it becomes a magnet itself. What an amazing thing to see, and yet, even with all of our understanding of physics, it still seems to strike at our ability to appreciate magic, unexplained things. We can see it, we can feel it, we see what it does. Is there any way we could get some power out of it? Well, there is, but not the way you might expect. There are a couple of simple rules for getting power using a magnet, and one of them is magnets have an interesting property. If you move a magnet by a conductor, if you change a magnetic field that's by a wire, you induce a current in the wire, and that's how every generator, literally every generator, works. You move a magnet around, and it passes by some coils of wire, or you move some coils of wire back past a magnet, and current ends up in the wire. But it takes energy to move the coils or to move the magnets. So what's really happening here is your movement of the object is providing the power. And that is combing free loose electrons and moving them through the conductor, making the current flow. So it's just like you turning a crank or a paddle. You're doing the moving, and the energy of your movement gets converted from mechanical energy to electrical energy. So the magnet is acting as the intermediary, the device that allows you to do the conversion. It's not generating power. It's the catalyst for converting it. And here is another very important point to make about the process. The magnet has to be moving, or the coil has to be moving. Because if the strength of the magnetic field, if the level of the magnetic field remains constant, nothing happens. So you can have coils of wire with a big magnet next to them, and nothing will happen unless one or the other or both are moving away or toward each other. There has to be a difference. It's sort of like something uphill and something downhill. If you have a ball on the ground and you want it to roll, and the ground is level, it's not going to go anywhere. You have to raise the ball or lower the ground in order to make the ball start rolling. The magnetic field has to be changing in order to generate a current. And this is the thing. Magnets, again, don't generate power. They allow you to convert power from one form to another. And a static magnetic field isn't going to do a thing. It has to be moving. So in all of these cases, you've got to supply the energy by moving something. Now, a lot of people have expressed the idea of taking a generator and using the power from the generator to run a motor, and then using the motor to turn the generator, in the idea that this would continue to generate power for you. Well, this doesn't work for a couple of pretty obvious reasons. Number one, when you turn a generator, you don't get 100% of the motion that you put into the generator out as electrical power. You generally get about a third of it. Call it 33%. Now, the power coming out of your generator then runs a motor. Well, motors aren't 100% efficient. If you got a motor that's 70% efficient, you're pretty lucky. So now your motor is running with only 70% of the power that you put into it. And this is going to run the generator that's only 33% efficient, which is going to run a 70% efficient motor. It's pretty easy to see that in the first shot, you're only going to get 23% of your power at best in each pass through the loop. In other words, about 75% of your power turns into waste right away, heat. And this is why you can't use a generator to run the motor to run the generator. Every pass that the current makes through the loop, it loses 3/4 of itself, or worse. Now, there are systems that can be very good, but not great. And why is this inefficiency? Why does it exist? Well, no mechanical system, no electrical system is perfect, and the bearings use up some of the energy as friction, and they heat the motor frame, and there's an equivalent of friction in magnetics. Materials saturate. It's called hysteresis. The material will pack up on a magnetic field as much as it can, as much density as it can take, and then everything past that point doesn't make a better magnetic field. It doesn't make a stronger field. It literally converts it to heat. So saturation and hysteresis effects in the windings and in the laminations in the generator and in the motor are eating part of the power and turning it into heat. Nothing magnetizes 100% efficiently. That's part of the process. All the field lines for the magnet are not trapped in the windings. That's another thing. Some of those are just passing through empty space. If you could confine more field lines, yes, you could get your better efficiency, but you would never reach 100% for all of these things that I've mentioned. So is there a way to generate power that doesn't use this method? Well, there are a number of them, and one of them is thermocouples. Now, a thermocouple is, put very simply, it's two different metals in the form of a wire or something twisted together so that they're in contact. And when you heat them, a tiny current is developed. Now, the issue with a thermocouple is very simple. You have to have a hot end and a cold end. In other words, there's your difference. Something's uphill, something's downhill. You have an energetic end and a less energetic end, and the current is flowing because of the difference between those two, the difference in temperature. If your thermocouple was all at the same temperature all around the loop, it wouldn't generate any useful current at all. But there are power systems that use this method, and they're called thermoelectric systems. And depending on what they're made of, you can actually get some pretty good efficiencies. Some of them can rival solar cells, and they're used for scavenging heat, bottom-end heat off generator systems, or for converting rather cheap heat directly into electrical power. The Russian military for many years carried small lamps or stoves that had thermal generators in the chimney, and as it ran, you could heat your food on it, and you could do whatever, and it would run the power from that through a small radio transmitter, for instance. So you had heat, you had a little light, you could cook, and you could run a radio. These are not unusual systems. They're typically not real cheap, but they're coming down in price because research is showing us better materials and more efficient ways of making them. Presently today, they use them on a lot of power systems where you need to get every bit of power out without a great deal of expense or any moving parts. So thermoelectric modules can do that for you with pretty fair efficiency. Now, another trend today is in a specific type of solar power called concentrated photovoltaic, or CPV. In this, what they do is they have a special type of cell, usually made of something like gallium arsenide and multi-junction, and they take the sunlight through a lens and they focus it into an intensely hot spot. And it goes through a device called an opalizer, a white sort of glassy material that spreads the light to a uniform glow. And that is used to illuminate the cell. Generally, it's right in contact with the cell. So a huge amount of sunlight is concentrated into a tiny area, and the cell converts that into electricity. Now, this makes it extremely hot, and normally these are water-cooled systems to prevent any damage to the cell. However, some entrepreneurs have taken the thermal conversion cells, the thermovoltaics, and placed them on the back of the photovoltaic cell, and of the waste heat, they can typically get about 20% of that or so converted to electricity as well. So let's say you get 35% of your initial sunlight as electrical power, and that's not unreasonable for a gallium arsenide multi-junction cell in a CPV system. So 35% of your sunlight gets converted to a usable electricity, while 65% of that is either reflected or waste heat. But if you can capture 20% of that, you get another 13% of your power back. So overall, your 35% and your 13% is 48%. You actually can get an extremely lucrative bit of energy out of this thing, and it doesn't take a huge amount of space, but it's running pretty much at the edge of what is possible right now in terms of temperatures and material durability. So from a practical standpoint, we actually have systems that can harvest enough power so that 2 square meters of collecting area could actually power your entire house indefinitely, as long as the sun is shining, and if you had a good battery system to back it up, you'd be in great shape. And of course, I've mentioned this previously in other shows that the big obstacle to renewable power is the storage systems we use, and that graphene supercapacitors and similar technology will probably be the thing that saves it and brings the cost to about half of what it is right now. And once we've done that, whether energy is free or not, it's effectively free, and that's close enough. But to get back on the track of the subject, there are many ways we can generate power without consuming fuel. But none of the systems that we've ever looked at has ever produced a greater yield than what you put in, with a couple of exceptions. Nuclear power, of course, generates a lot of energy, and anywhere from 10 million times the density of chemistry exists in nuclear reactions. So there's a great push to use nuclear power, because when you generate power that way, it takes so little fuel to generate an incredible amount of power. It's an extremely attractive, not to say even seductive way of making power. And there are political issues, not so much technical issues. The big issue with nuclear these days is the law makes it illegal to recycle the waste, so we have nuclear waste. And that's very easy to dispose of. It's very easy to process and turn into something that isn't nuclear waste. But that's a political issue and not a technical one. The other issue is people who are operating the plants often ignore the warnings that they're given when something goes wrong, and this leads to disasters. Literally every disaster we've had has been because maintenance wasn't performed or somebody didn't listen to the alarms. The technology itself certainly could be better designed, and we do have those designs. They're not being built. And, you might be able to tell I am rather pro-nuclear, because there's a lot we can do with it very cheaply. And yes, we do know how to handle the waste, and we do know how to make it safe, but it just isn't being done. And we've got to know why. We've got to hold people accountable and make things happen. But there isn't even, in a lot of cases, a need for that sort of density. If we actually build the storage systems that I've spoken of, we would have all the energy from the environment around us that we would need in the form of wind and sun and geothermal and other forms that are around us all the time that we sometimes don't recognize. But do systems produce more than unity, more than 100% output? There actually is a system that does that, that isn't nuclear, and we will talk about that very shortly here. I want to wrap up with a couple of statements about how we do have the methods of generating all the power we'll ever need, and that the sun alone could run the entire planet, and we don't have to put those collectors on the ground. If we put a solar collector on the ground, it only gets 1/3 of the sunlight that you would expect on the ground. And that's because of the day-night cycle. You have to make them track the sun, and there's losses at the beginning and end of the day. But if it were in orbit, you generally get from 4 to 5 times as much out of a solar panel in space as you do on the Earth. So there's a great incentive to put them in space and generate huge solar farms in orbit, solar power stations, or orbital solar power, space-based solar power, it's sometimes been called, and to beam this energy back to receivers on the ground. And it wouldn't cost that much. I mean, look at the trillions we've spent in waste and in warfare, and it wouldn't cost anywhere near that much to make our entire nation, in fact the entire planet, independent of fuels. That can be done right now. We know how to do it. We have the technology to do it. We simply have to get off our tails and do it. We have the ability. So we're going to talk a little bit about this amazing system that generates more power or generates more output than what's put in. And we're going to look at what it does and how it does it, and if it is really of any use practically, because that's the bottom line right there. Can we do something practically with it? And we're also going to look at something called Maxwell's Demon. We're going to look at a century-and-a-half old problem involving heating and cooling and decisions and information and entropy. It's going to be an interesting chat, and one that's going to tell you some things that you might not have thought about. And that's what we're here about, provoking your thinking and giving you new things to consider. This is Talk Universe. I'm Sir Charles Schultz. Imagine the following scenario. You have a box full of air and next to it another box. And you have control of a tiny valve that's big enough to allow a single molecule of air to pass through into the other box. Your job is to watch each molecule as it approaches the gate, and if it's moving fast, you open the gate and allow it to escape into the other box. If it's moving slowly, you keep the door shut, and the slow-moving molecule bounces off and remains in the box. After a while, all the fastest molecules will end up in the empty box, and all the slowest molecules will end up behind. What happens is, the box with the slow molecules gets colder, and the box with the fast molecules gets warmer. This is known as Maxwell's demon, the ability to decide which molecules should pass and which ones should remain. It seems like it's possible that you could violate the second law of thermodynamics, that entropy always increases by operating such a system. But this isn't to be. James Clerk Maxwell was a physicist and a scientist, and he is the father of electromagnetic theory. His equations stand today. He had this idea about entropy. The second law of thermodynamics states that entropy or disorder in a system always increases. Things run down, in other words. But in 1867, Maxwell thought of an experiment which might violate the second law of thermodynamics. By using the Brownian motion, the random molecular motion of a fluid such as air, and using a selector, Maxwell's demon, which would decide only to allow the fastest molecules to pass through the gate, he could see that all the heat would end up in a separate box, and all the cold, the lack of heat, in the initial box. Now, in reality, this doesn't actually happen, and a lot of experiments have been tried to see why and how we can possibly put it to work. After all, if you could make a system generate its own hot and cold without the use of energy, simply by making some decisions, you'd be ahead of the game, right? And people have made devices like molecular ratchets, tiny devices that will move in one direction only when hit with the random movement of the particles around them. And these devices do, in fact, seem to run entropy backwards to a degree, but they don't actually. You see, they actually increase the disorder in another part of the system somewhere. So while molecular ratchets have gone from a 50-50 mixture of hot and cold to a 70-30 mixture driven by nothing more than the molecular motion around them, they don't actually decrease the entropy because there's a cost somewhere else in the system. After doing the experiments and building the hardware and seeing what really happens, what it really comes down to is this: the act of making a decision takes energy. In other words, information, processing, and decision-making all consume energy and have an equivalent mass. Strangely enough, it turns out that information is a wedded-in part of the space-time continuum. So when we talk about entropy and information and energy, we're really talking about the randomizing, the running down, not just of energy, but also the configuration of the information in the system. Now, the upshot of this is a new class of computation has been designed that does not consume power as a result of this information rule. And what they do is they create the answer, which is a certain set of information, and the anti-answer. They worked out logic gates that perform their functions in a manner that the results are reversible. So the information ends up in one place and the anti-information ends up in a sink someplace else. And in a sense, you've compartmentalized the information in such a way that it can make it appear that you've gotten your computation done for free. Now, the reason this is important is because if you can get free computation, then you have a means of powering Maxwell's demon that doesn't consume energy and increase entropy in the system. In reality, there is a change of entropy, but it's something that in a sense can be managed in a certain way. So in some restricted cases, it may be possible to create systems that appear to live forever without using up their power source and without increasing the local entropy. Such a system would actually be very useful because if the ideas about uploading human minds into a computing medium work, then you'd have the ability to create a medium in which the human mind could exist for, effectively, an endless period of time. But what if we started making tiny devices that were frictionless and wearless and would last forever, were tiny, let's call them perpetual motion machines that never wore out and never stopped? What if we made tiny components like that and we built our systems out of those? Could we make a system that then would run forever and would never need repair? Unfortunately, it doesn't work. I'll explain why. You see, an atom is a tiny, immutable, perpetual motion machine. The electrons orbit it without friction. They actually have a sort of a cloud in layers, like the skin of an onion, the layers of an onion. And that's where the electrons exist. They don't run down, they don't have any friction. The core of the atom, or the nucleus, has components that don't change. Most atoms are pretty stable. They don't undergo radioactive decay, and they don't break down over time. Something made out of atoms, you would think, which are frictionless perpetual motion machines that never wear down, would probably be the ideal thing to use. And yet, when we put a number of atoms together, something funny happens. Wear emerges, changes emerge. Irreversible changes occur to things. The wearing down, the running down, the breaking of chemical bonds, the reforming in ways we didn't plan. And this is entropy. This is the running down of our universe. So making our devices out of ageless, deathless parts that never wear out really doesn't do any good, because when enough components get together, it's always possible for their structure to be rearranged in a manner we didn't anticipate. Things will break, things will shatter, things will wear down, things will deform. Entropy is this breaking of order, this destruction of order, the wearing down, the using up, and even the whole universe is running down. Ask yourself about the stars. Where does their energy come from? The universe initially was made of a great deal of hydrogen, and the hydrogen is forming the stars. The stars are consuming it. They aren't just heating it up. The stars actually transform the hydrogen into energy through fusion and then into helium. At the end of their life cycles, the stars explode, often scattering new elements to the space around them. These elements are the things that are used to form the planets and the next generation of stars. The universe is using up its fuel supply. Now, when we look at it, there are a few ways the universe can eventually run down or run out of energy. One is stars form, burn the hydrogen, explode, and after a few cycles there's no hydrogen left and there's nothing to form new stars. After a while, the universe spreads out, gets thin and cold, the starlight fades away, everything gets cooler, colder, and over the intervening trillions of years, the end of the universe as we know it comes. And it's what they refer to as heat death. The basic destruction of the order, the running down, the entropic end of everything. So once the hydrogen is exhausted and there's nothing more to power the stars, new stars can't form. New planets can't form. Everything basically runs out of power. Unless we find something to replace the natural sources of energy that run the stars and keep the universe moving, there won't be anything to keep the universe alive. And that means there won't be anything for human beings to live on. Now, this seems like a bleak prospect, but there is always energy in a system, and the randomness beneath the vacuum itself may be where we find our solutions. You see, the universe is a geometric thing, but at the tiniest level it isn't flat and smooth and hard like a sheet of glass. It's actually chaotic, boiling with energy. This is Wheeler space, and it's as small as 1 × 10 to the minus 34th meters across. In this tiny void, there is boiling energy everywhere, randomness, the white noise in the basement of the universe. This is the stuff of which the bottom of all movement of particles and energy is formed. This is called the zero-point energy. Zero-point energy is responsible for all energy and fields and forces existing. Without it, everything would be static and unchanging. It would be like trying to move through a plate of steel. Very unlikely. And yet everything at the quantum level, down in this space, happens in a probabilistic manner, like the toss of a coin or the throw of the dice. And the Wheeler space energy, this zero-point energy, boils and explodes into being and then vanishes again. Think about it like a tiny bank loan. You'd borrow a little bit of money and then you have to pay it back soon. But there's a simple rule based on something known as the Heisenberg uncertainty principle. And it's this: the more you borrow, the faster you have to pay it back. If you borrow a little bit, you can hang on to it for a little while before you have to pay it back. So there's an inverse proportion between the amount of energy that appears and how long it can hang around before the debt has to be repaid. You see, nothing stays permanently this way. Whatever you borrow must be returned. But if particles couldn't borrow this energy, nothing could move, information couldn't flow, and the universe would be frozen in time, unable to change in any way whatsoever. It would exist, but it would be a timeless place, unable to have any sort of change. No entropy, no age, no development, no fusion for the stars to run from hydrogen. Nothing would happen at all. So an important principle of zero-point energy is this. You can't extract it, you can't use it, you can't do anything with it, but it is the thing that catalyzes the movement of time, the change all around us. But recently, two things have occurred in physics that point to the possibility that maybe the zero-point energy is useful in some other ways. The first refers to something known as the impossible space drive, or the EM drive. What happens here is a beam of microwaves is focused into a cavity shaped like a cone. For some reason, a tiny thrust is produced that has no reaction. This appears to violate one of our fundamental laws of physics about movement. What's interesting is researchers who are looking at the system think that it's possible that the microwaves are accelerating tiny virtual particles that emerge from the vacuum due to the zero-point energy, and then the particles are vanishing again and carrying this momentum with them. In other words, the drive is pushing on a ghostly part of space-time, which then vanishes, meaning that the need to throw something away to create a reaction, such as acceleration or propulsion, no longer exists, at least on a small scale. If the theory about this is true, then the zero-point energy is directly responsible, in a sense, for creating a drive that moves without the use of fuel and throws away nothing in the process, which is truly a fascinating finding. But there's a second event that happened a couple of years ago that very few people are aware of. When engineers were designing new LEDs, or light-emitting diodes, they were playing with very low-energy inputs to these LEDs, and they found that certain types of crystal actually seemed to harvest some of their energy from the random thermal energy around them. When they were measuring the amount of light coming out of the LED versus the amount of power they put in, they found that they were getting an operating efficiency of 231%. Now, nothing we build even runs at 100%, so this was truly an astounding finding. What it means is this device is capable of harnessing some of the normally unreachable energy around it and actually doing something useful with it, producing light. But don't run out and start putting your stock in it. It only happens at a few microwatts or millions of a watts of scale at this time. A lot of further research is needed to see if this is something that can be turned into a useful product that uses a tiny amount of current to act as a catalyst and then derives the rest of its energy literally from nothing. Now, in these two cases, there's some fairly good physical evidence at this point, and experimental evidence as well, that these devices are actually tapping into the randomness, the white noise in the basement of space-time to actually operate. And if something like this can be done, then yes, it may be possible to harness energy for nothing. But the devices themselves are extremely delicate usually, and hard to make and hard to maintain. The effect is only beginning to be understood now, and a great deal of work will be necessary in order to see if we can actually do something useful with it. But it does indicate that it might be possible to harness the energy around us, even in the form of low-level heat, and do something useful with it. One very important criterion to recognize that these devices do exhibit, and none of the other things you read about in the back of the magazine covers do, is this. It's clearly demonstrable that they're harnessing power from somewhere that doesn't come from fuel and doesn't come from the consumption of something. It's actually harvesting energy in each case from something in the environment. In the one case, it's the momentum that they're harvesting by pushing on virtual particles before they vanish, and in the other case, it's the random thermal energy that the crystal is harvesting to produce some light. But for all of the devices that you see advertised that are supposed to run your home or provide free energy, not one of them has ever provided the very basic premise in a concrete and measurable form, and that's this. Do any of the people making those devices run their utilities with them? Unless you actually see the device producing power and in use by these guys, you can be pretty certain that it's something that just plain doesn't work. Don't fall for the hype. Try it for yourself, and be skeptical. This is Talk Universe. So let's take a quick trip down the list of free energy devices and look at a few of them that you might encounter. All right, magnetic motors. Everybody shows some video of some devices with a number of coils and a bunch of big blocks of copper or aluminum and claim that it's generating a lot of power. Well, all you have to do is hook one of these things up to a light bulb or some sort of a load and see if it actually runs it and for how long. And you have to know that there aren't any batteries in the thing or it's not plugged in the wall or doing anything like that. You see, videos are notoriously easy to fake these days. Everybody's great at computer graphics or knows somebody who is. And people pull tricks on people all the time, and if it means that they can make a little money off of you, it's quite likely that's what you're seeing. There's always the system that's just a little ways away. It's just around the corner. We're only a few months away from making this thing work. Those are, to be honest, people have been working on these things for years, and unless they have some basic underlying physics behind it that is at least plausible, then it really isn't even worthwhile looking at an investment in such a thing. Keep your money in your pocket, because unless they can show you a theory that works, unless they can show you some reasonable hardware, some expectations, something convincing, it's probably not going to happen, because the conditions that exist in nature run the whole ballpark, everything you can imagine. In the core of the Earth, in the interior of the sun, on the surface of a planet, all of the conditions that you can think of occur somewhere. Just to put that into perspective, somebody discovered that laser light, which is considered to be an opportunity to spot technology, an artificially generated thing, laser light was being seen edgewise coming out of the atmosphere of Mars. It turns out that under the certain conditions that exist there, sometimes sunlight or other conditions can pump the atmosphere to actually produce bursts of laser light. Now, this is an unusual phenomenon, but the laser light they were detecting was definitely a laser, and yet it was a natural phenomenon and not a man-made one or an alien-made one. So the conditions for just about everything exist in nature somewhere, and if something could generate a lot of energy, something in nature would be doing it, and we'd spot that. That's one of the first things to think about. Magnetic motors, anything that has a magnet in some sort of a wheel moving around under its own power, no. They precisely balance some magnets, get the thing to roll for 3 or 4 or 5 minutes sometimes, but it's running down, and it isn't generating any power. The moment you put a load on it, it will come to a stop. So those things are they're a no-show. I've seen numerous types of machines where they have compressed metal powders put into forms of magnets and bars and geometries, and none of them really work. And again, anybody has the opportunity to go in there with a power meter and a voltmeter and a current meter, turn the thing on and take some readings and see what's really happening. So unless somebody actually demonstrates one of them, it doesn't work. Okay, I've seen systems where you inject water that's been electrolyzed into hydrogen and oxygen into an internal combustion engine, and you get better efficiency out of it. Now, this is one that actually, under some circumstances, can work, and there are reasons for that. Many years ago, when jet engines were first being played with, one of the things they discovered was that if you injected water vapor, water droplets, into the engine, it would literally explode into steam and produce an immense burst of thrust. So injecting water in the engine did actually give the heat a leverage, like a rocket, and it would increase the thrust. Now, it was horribly inefficient in terms of fuel, but boy, it did the job. In the case of an internal combustion engine, if you run the engine on pure hydrogen, it will run just fine. You make some adjustments to the fuel injection or the carburetor if you have one, and hydrogen is a wonderful fuel. One of the difficulties you will have is this. Burning pure hydrogen can produce a great deal of heat above and beyond what you might expect. If the atmosphere were just oxygen, then burning hydrogen would produce nothing but water vapor and be absolutely clean. But the atmosphere isn't pure oxygen. It's a mixture of nitrogen as well. And one of the first things that happens is the temperatures you reach with the combustion of hydrogen and oxygen can also inadvertently burn nitrogen in the process, and you get smog. So you have to control the temperature the engines burn, the amount of oxygen it's getting, etc., very cautiously in order to not produce nitrous oxides in your exhaust when you're burning pure hydrogen. So that's an issue. Now, with the systems that electrolyze the water into hydrogen and oxygen, electrolysis in this basis is a losing proposition from the start, and that's something that you have to know. you're only getting about 20% of the energy out of the process that you put in the form of hydrogen. However, if you're injecting the hydrogen and oxygen both into the engine after it's been electrolyzed, there are some curious things that can happen. And one is you can get a different type of combustion that produces different products than you would normally get when burning fuel in air. And there's some pretty good evidence that there is an increase in power in this case. Will it work for you? Well, that depends. It depends on a number of things. Internal combustion engines are very well known, but there are some conditions in some of them that are hard to define, and it requires a lot of advanced equipment to see exactly what's happening. There were experiments done a long time ago with hydrogen and oxygen being separated into something called Brown's gas and then combusted again in the cylinder, and it had some interesting properties. And one of them is I saw a torch that looked very much like an oxyacetylene torch, but it was burning this hydrogen and hydroxyl, and it was producing a flame that appeared to be cool to the hand and yet would slice through metal. Amazing, anomalous stuff. Very interesting and easy to reproduce, something that a lot of researchers don't seem to have really done a lot of work on. So it doesn't surprise me that when you inject something like electrolysis products of hydrogen and oxygen from water into your engine, you're going to get some sort of a change in the chemistry, which could very well give you more energy. Some people are getting pretty consistently better mileage out of the system, and I know some people who actually make these systems. So I'm not going to give a negative to this. I'm going to say, tentatively, they look like the real deal. It's just that you're not going to get a huge increase. Just keep that in mind. When you're looking at systems that produce electricity from magnets, the magnets have to be moving, or the conductors have to be moving, or it's plain just won't work. You're not going to generate anything. And I can tell you, I've built a lot of hand crank generators and motor generator systems, and I know a lot of people who've done a lot of research in it. This is not magic. We know exactly why they work, and we know what they won't do. Thermal electric systems. Yes, it's possible to harvest heat, but you generally need pretty high quality heat. They make a number of systems called OTEC, Ocean Thermoelectric Converters, that read very well when you look at the input energy and the output figures. They have about 35% generator efficiency. They measure pretty favorably in terms of generating power from the temperature difference, the thermocline, the warmth of surface water, and the coldness at the water depth that they have the other end of the thing planted. They're long floating buoys. They use the heat of the surface water to boil a working fluid such as propane or ammonia, and that vapor runs a turbine, and the cool end down at the bottom where the cold water is what generates the differential. So you can harvest an awful lot of energy from the oceans using these, and they were built in the 30s and they work very well. With our technology today, we should be able to make them quite successful. There are other systems, the energy harvesting systems I mentioned, the voltage generators that run on heat, the thermovoltaic modules, which are quite similar to solar cells, but they run on heat. Yes, they do work. They're a little expensive. The efficiencies are getting pretty good, but they do work. And, you're harvesting energy that's heat. That's about as free as it gets if you're using something like sunlight and a lens, or the difference in ground temperature, or something that's easily available to you. When you start looking at systems that harvest the wind, you can argue that that's free energy because it's not costing you anything other than the piece of hardware. And I think we need to look at this term as well. When people start talking about free energy, most of the time they're talking about generating it magically out of nothing or pulling it out of the void, zero-point energy. Let me give you a hint. Nothing harvests zero-point energy at this point. It is basically... think of it as science fiction. Until we get something that actually works, such as those LEDs I mentioned, or such as the EM drive, which is being tested now, and it does seem to work, then somebody's pulling your leg. If you go out in your garage and start building things, the chance that you're going to build something that's going to violate the laws of physics as we know it is extremely slim. You have to have a theory. You don't stumble across these things by accident, usually. There's an old saying that I heard, and it makes a lot of sense. The greatest discoveries in science rarely are arrived at with somebody yelling, "Eureka!" Most of the time, it starts out with, "Now that's odd." Somebody notices something that doesn't seem to square, and they do some experiments, and they find something they didn't expect. So the big experiments, the big discoveries start out with, "Hey, that's strange," not "Eureka." There are other systems as well that do generate power, and I think when we start talking about free energy, we need to realize that any energy you can harvest that doesn't cost you anything to generate, that is around you all the time and easy to get, should be considered free energy, because after all, you're not paying for the fuel. And make no mistake, we have plenty of free energy around us. The wind, the sun, the sea, the movement of water, the ground geothermal reservoir. And geothermal is a pretty good contender. I'm in a place right now where they're doing some drilling for boreholes to look for the heat of volcanism. And that volcanic heat could very well power this island. And that's a process that's been going on for a number of years. And it's had a number of setbacks financially and logistically. But I think they're reaching a point where they're ready to start putting a generator here. And once that occurs, then you know that as long as the Earth has heat inside it, and it's been doing it for 4.5 billion years already, nonstop, then you can be pretty certain that you'll be able to harvest that for an incredibly long period of time, as long as you keep your system clean and all the components maintained. I imagine that when you look at Iceland, and a lot of people are just salivating, man, if we could get power like Iceland has, they're like 95% or better self-sufficient, and they run almost entirely on geothermal energy. Now, they're in a special situation, obviously. You can't always harvest geothermal energy in that density. But a lot of people use tunnels underground. They run air through, and the ground heat reservoir heats or cools that air, and that's a very interesting and low-cost way of harvesting geothermal energy. Just imagine if the ground temperature under your feet stays at a constant 65 degrees Fahrenheit year-round, and it's 95 outside, and you start running this air tube, and cool air is coming out of the ground. Well, look at all the edge it takes off your energy bills for air conditioning. But that very same air at 65 degrees Fahrenheit is going to be a real boon in the winter when it's 25 outside. So the ground heat reservoir is definitely a free source of energy for heating and cooling, and it can work all the time. I was told about a fellow who put a huge box under his garage when it was being made and filled it with sand and started packing heat in it from a solar thermal collector during the days. And then all your winter long, I should say, he harvested that by running the working fluid through it and taking the heat out of the sand. What a fascinating idea, and it certainly is a workable one. So what I'd suggest is look at the physics behind things. Nothing is magic. We know why things work. We know how they work. And if you hear a claim that's too generous and unbelievable, it probably is unbelievable. This isn't magic. It's physics, and we know where energy is. We know how to get to it. And yes, we're making some fascinating inroads in quantum mechanics. We will see some inventions very soon, I'm sure, that'll do things we didn't expect. And that's just in the nature of science. We always discover something new. But very few things are going to pull the foundations out from under us. Now, I do want to mention one other thing. It's no secret that I've done some research in cold fusion, and a lot of people are naysayers and don't believe it works, and they don't understand what's going on. And I have to tell you, it definitely does work. The issues are getting it stable and repeatable, and also getting enough energy out of it to make it worthwhile, because most of the systems seem to run right on the edge of melting down or not at all. So don't dismiss it. It does work. I can tell you that personally. For the most part, our lives do not change fundamentally. The toys get a little more interesting and sometimes a little more dangerous or expensive. But everything is pretty much as it was at the beginning of the world's history. So if you think about free energy, don't think about magnetic motors or zero-point devices or something like that. Think very firmly about harvesting the energy that comes to us for free all around us, because it costs very little. We can definitely do it, and it could be the thing that saves us. So what I'm going to say in closing is this. It's easy to be gullible, but we can't lose our sense of imagination. We can't lose our sense of wonder. At the same time, we also have to be skeptical. Walking the middle ground between completely skeptical and completely gullible is a tricky proposition. We have to learn some things about the world around us. We have to learn some physics. We have to understand how things work. Because this is a very complex world, and everybody's trying to make a buck. We do live in an age of wonders, and the world is becoming a better place, no matter what you see on the news. People's hearts still work, and our creativity still works, and it will work out fine in the end. This has been Talk Universe. I'm Sir Charles Schultz. Good night.